Maya is a research project funded by the European Union in the Clean Sky program series that aims to reduce the weight of aircraft manufacturing. The objective is to replace the thermoset materials by thermoplastics materials in interior cabins in order to decrease the weight of aircraft and improve the recyclability of the materials at the end of life of the product. The project itself is a manufacturing path for our topic manager, Dell Aviation, which is a German aircraft OEM, original equipment manufacturer. They do manufacture cabin interiors for aircraft. With two other laboratories, Lightat and Amadé, we have been able to set up a plan in order to make this transition from thermoset to thermoplastic possible. Alongside Dell Aviation, Lightat had the responsibility to choose a product which to apply our methodology and our manufacturing path. The chosen product by Lightat and Dell Aviation is a bracket for assembling the interior panel component of aircraft. The current design is actually a single design that is used for several aircraft models and adapted on each surface depending on the manufacturing method. The current manufacturing method of Dell Aviation is thermoforming. The thermoforming of composite panel are curved into a tool where we align different skin materials, a core, which is a honeycomb, and another skin material. The exploration path for the next product of Dell is going to be a polycarbonate with glass fiber. The main challenge of this research topic is going to be on one side the manufacturing, but as well the adhesion of the thermoplastic and the thermoset materials in use on the panel itself. The current method for the brackets is injection. Injection molding requires a tool that is going to inject a large amount of the same geometry that has to be adapted for each and every single aircraft model. Our role as IPC was to explore the different manufacturing methods outside of injection, such as additive manufacturing. Additive manufacturing allows a flexibility in processes choice, in material choices as well, especially the one used for aeronautics use. If you look at FDM, which is a fuse deposition modeling, for instance, we are able to actually put virtually any kind of materials that we want inside the machine in order to apply it on the composite panel itself. The complexity that we have to face and the challenge itself was a good adherence on the skin from the composite panel. The project was built on three axes. The first one was choose the materials that was validated for aeronautics use. The second one was the manufacturing, and the third one was the testing. The material choice is important because in additive manufacturing as well as injection molding, it is going to determine what are the rules of design and what is the limitation in terms of geometries, weight, and process that we are able to achieve. That part was led by Lightat in Spain, who has been responsible for the design as well and the topological optimization of the design itself in order to reduce the weight of the chosen geometry. The topological optimization is going to be computerized based on the forces that the interior panel has to withstand. The forces are going to be applied to different directions with a given value, and it's going to eat up the materials around the geometry in order to reduce the weight and improve the feasibility in processes such as additive manufacturing. The design for additive manufacturing is an important factor for feasibility of these parts. With this topology optimization, the material chosen has to withstand the different standards as well for fire, smoke, and toxicity requirement. IPC has been responsible for the choice of manufacturing methodology, whether it comes to injection molding or additive manufacturing. Additive manufacturing is a constellation of processes. It goes from fuse deposition modeling to sintering. In this very case, because the material choice validated for aeronautics is so limited, we decided to go for one of the cheapest methodology and one of the most widely distributed one, FDM. FDM allowed us to make polyethylamide and polycarbonate materials that were respecting the fire and smoke toxicity requirement in order to manufacture the parts. We chose to go in two directions. First was the injection molding, where virtually any thermoplastic is also feasible, and to back inject directly onto the skin material of the composite. The first step was to simulate injection molding. Based on the simulation result that we obtained, we have seen that we could not inject directly onto the composite panel as it is rather weak to compression. The pressure involved into injection molding is much higher, and we had to decide to go for injection on the skin itself. It was an opportunity though, because we could explore a little wider possibilities with the tool that we manufactured afterward. When it comes to the tool, we actually had to design the entire parts and assembly, and then mount it on the machines and start injection molding. We took the opportunity to have thermography available to stabilize the process with a thermal camera. With the same tool, it was also possible to inject standalone parts that were not injected directly into the substrate. Later on, these parts would be glued or welded onto the surface of the substrate itself. The second choice of manufacturing in additive manufacturing was actually FDM. We decided to go for two methods. Very much like injection molding, FDM allowed us to print directly onto the substrate or print a standalone part. The advantage of FDM in this case is that we did not need a tool. That means that we could do design iteration very fast. The challenge of FDM is the amount of parameters that can be tweaked in order to get the right part, and we know that these parts are anisotropic. The performances will change according to the manufacture method and the toolpath that will be taken by the machines. Additionally, the material that we are going to use have a very high tendency of shrinkage because they are very high performance. In these optics, we had to find methods in order to improve the adhesion of the models onto the substrates, very much like injection molding. The temperature could be controlled into the chambers for printing. That would mean that eventually the direct manufacturing of parts onto a substrate has to be done directly onto substrate prior to the thermoforming of our aircraft panels. Non-planar deposition is actually a planar deposition where the plane where we depose the material is actually tilted in strategic places. Using this tilted angle allows us actually to depose materials in places where we would have need support materials in the first place, but that we do not need anymore. On top of that, we have noticed that it was possible to improve the mechanical performances by locally changing these planes. With a higher surface of contact, the stress is more distributed in strategic places. One last process was barely explored. It's the indirect manufacturing. As such, injection molding requires a steel tool, but steel is expensive when it comes to manufacturing a geometry. Therefore, it is important to have the right design and the volume associated to the steel tool. In order to make small series with a decent volume that can still be done in injection molding, we decided to test injection molding into polymer tools. IPC has developed an expertise in tooling for injection molding, in particular regarding polymer tooling for polymer injection. After we had found the different processes available for manufacturing, we had to go to the third axis of the project, which was the testing and characterization of our manufacturing methods. This part was handled by Amade, the material laboratory from the University of Girona in Spain, where they set up a jig and fixture for the different design that we wanted to test. The first part of the testing was to characterize the materials that we had chosen. The second testing phase was to actually test the bracket geometry itself after topological optimization. In this very case, we had two phases, but only phase 2 was tested. Phase 3 was waiting for different approvals afterward. The final test of this part is going to actually be the fatigue test. Stressing the parts under different dynamic cycles allowed us to measure what was the adhesion after a number of cycles. The overall result showed that every manufacturing path is actually technically correct. Now the question is, which one is economically viable for our topic manager? Since this is an exploration, our job now consists in giving the topic manager all the information necessary to assess the economic impact of such a change. But beyond the economy, we are looking into reducing the CO2 amounts by reducing the fuel consumption, by reducing the weight of the aircraft. Reduce the CO2 in the atmosphere, clean up the sky.